Chapter 2, Trigonometry, Lesson 1, Part 1, and Introduction to Radians. So up until now, we have used 360 degrees to represent one full turn. You may have said in the past there are 360 degrees in a circle, 180 degrees in a half circle, 90 degrees in a right angle. But why is it that we've used 360 degrees to represent one full turn? Why not, for instance, 100 degrees? That's another nice round number. And the answer goes back to Babylonian mathematicians who actually chose to use 360 degrees because they used a number system which was based on the number 60, unlike our number system, our modern day number system, which is based on the number 10. Another reason is that 360 degrees is a highly composite number, which means it has a lot of factors. It divides by 2, 3, 4, 6, 9, 12, all these factors, which make it very, very simple when doing angle calculations. But actually, it's a completely arbitrarily chosen number that actually has nothing to do with the true properties of a circle. So we have to ask ourselves whether, as we learn more about maths, as we learn more advanced maths, is 360 degrees the best unit of angle measurement? And the answer is, when we're dealing with trigonometry and when we delve further into the calculus, so learn more about differentiation and integration, actually we can't always use 360 degrees and the degrees measurement when we're dealing with angles. We need an angle measurement which actually relates directly to a circle. And that's where this idea of the radian measurement comes in. It's an alternative angle measurement which relates directly to a circle. And we're going to introduce it today and have a look at how we can calculate some angles in radians and how we convert between radians and degrees. So what is the relationship between the two? So I want to start off with a sector from a circle. So you can see the sector here. I'm going to label point O, point A, and point B. So hopefully you can all see very clearly sector O, OAB. Now, we're going to give this sector some particular properties. I'm going to say that if this is the radius here from O to A, which of course is also the radius here from O to B, if I can set it up so that the arc length from A to B here is also R, then the angle here, theta, is defined as being 1 radian. And that's how we define a radian. It is the angle created when you construct a sector so that the arc length of the sector is the same as the radius of that sector. Now, we sometimes write 1 radian as 1c, and the c stands for circular measure. Which basically tells you we're dealing with radians rather than degrees. Now, instead of just thinking about a single sector like this, let's expand the idea to a whole circle. So essentially, imagine expanding that angle theta so it rotates all the way around and actually your sector becomes a whole circle. What's the arc length of a circle? Well, it's equal to the circumference of that circle, which is equal to 2 pi r. But what's the angle of a circle? Well, so far, all we know is that the angle of a circle, which is 1 full turn, is equal to 360 degrees. Because at the moment, we don't yet know how many radians there are in a full circle. But can we combine these two facts to find out what the angle in 1 full turn is in terms of radians? Yes, we can. So let's think about the sector. to start off with. What was the arc length of our sector? Well, the arc length of our sector was equal to r. What's the arc length of our circle? It's 2 pi r, because it's the circumference of the whole circle. So look at what's happened between here and here. To scale up the sector to a full circle, we multiply by 2 pi. Now, what about the angles? Let's think about those. What's the angle of our sector? Well, remember what we said. If we're talking about a sector where the arc length, r, is the same as the radius, r, then the angle of that sector, theta, is equal to 1 radian. So the angle of our sector is 1 radian. Well, if we're scaling up our arc length, multiplying by a scale factor of 2 pi, then we've got to scale up our angle by the same factor and also multiply by 2 pi. So that tells us that in a circle, there are 2 pi radians. So one full turn, 360-degree turn, is the same as 2 pi radians. So let's just repeat that. The angle in one full turn, i.e. the angle in a circle, is 360 degrees, or we can say it's equal to 2 pi radians. And you see here how, by using the radian measurement, we actually link the angle to something related to circles. We know pi is related to circles. So we can say that 360 degrees is equal to 2 pi radians. And this then allows us to convert other angles in degrees into radians very easily. So for instance, what would 180 degrees be in the radians measurement? It would be pi radians. What would 90 degrees be in the radians measurement? It would be pi over 2, which we sometimes call pi by 2 radians. What would 45 degrees be? It would be pi by 4 radians. So we can convert any measurement in degrees to a measurement in radians and vice versa. Could we write down a rule that would help us do that in a general sense? Have a think about that. So hopefully you've spotted that if you want to convert from degrees to radians, the simplest way of doing this is to divide by 180 and then multiply by pi. Think about this example here. 360 divided by 180 is 2, multiplied by pi gives you 2 pi. So divide by 180 and then multiply by pi. And then, of course, if you want to work that backwards, going from radians to degrees, you simply do the reverse. You divide by pi and then multiply by 180. And again, you can see that using this example here. What's 2 pi divided by pi? It's 2 multiplied by 180, and that gets you to 360. Alternatively, you could think about it like this. You could simply say, to go from degrees to radians, you multiply by pi over 180, which takes the two calculations of divide by 180 and timesing by pi as one. Or to go from radians to degrees, you simply multiply by 180 over pi. And then that takes into account the two calculations of dividing by pi and multiplying by 180. So that's how we can do a conversion. And what you're going to do in a minute is practice converting between the two types of angle. So have a look at the tables. Using the conversion strategies that we've just discussed, you're going to convert all of these angles in degrees to angles in radians, first of all, on the left-hand side, and then on the right-hand side, you're going to convert all of these angles in radians to angles in degrees. The answers will come up in about 3 seconds, so make sure you pause, have a go at this yourself, and then check your answers. Rewind if you need to, and look at how we carried out the conversion suggestions in the previous slide. So here are the answers to the first set of questions. You can see they're all fractions of or multiples of pi. Now, just a few things to point out. If you look at this example here, 270 degrees, sometimes we might write it as a decimal multiple of pi. So rather than 3 over 2 pi or 1.5 pi, we might write 1.5 pi. Both are acceptable. People sometimes worry about whether they are writing out angles in radians correctly. So to give you an example, 120 degrees, 2 pi over 3 or 2 pi by 3, which is how we would say it, is absolutely fine, and so is 2/3 of pi. So you can see the different ways in which we can write the same angle correctly. So here are the answers to the conversions from radians to degrees. Now the last one is quite interesting because you have 3/7 of pi, and because 7 doesn't divide exactly into 180, you don't end up with an integer angle in degrees, you end up with this angle here, which of course we'd have to round if we were presenting that as some kind of final answer. So that's an important thing to remember, that angles don't necessarily have to take neat integer values. And we're going to explore this in a little bit more detail in just a minute. Now, all of the angles that we've looked at so far in radians have been exact multiples of pi. Now, a few of you may have been wondering about that notation I used earlier on with the little c, which represented circular measure. Now, if an angle is presented as a multiple of pi, then automatically, because of the presence of pi, we know that we are dealing with an angle in radians. So you could write, for instance, 2 pi c, to really be very clear that you're working in radians, but you don't have to. You could just write 2 pi and say 2 pi radians, or people will know that you are talking about angles in radians. Now, what happens if you have an angle in radians that is not a multiple of pi? So what about an angle 2.5c? Now, the presence of the c there helps me know that this is in radians, or I can write 2.5 radians. And that then gives me full clarity that my angle is in radians. But what would this angle be in degrees? So let's look at our little conversion calculation over here. So I want to take 2.5 radians and I want to convert it to degrees. So 2.5 radians is equal to 2.5 multiplied by 180 over pi. And what does that work out to be? It works out to be 143.239 ... degrees, and we must use the degrees symbol for perfect clarity. So 143.2 degrees to 1 decimal place. So really it's very much worth remembering that not all angles in radians will be exact multiples of pi. So we must be very clear with our notation. If our angle is in degrees, it's very obvious. We write a degree symbol as you've been doing for years and years. If your angle is in radians and it's a multiple of pi, that's absolutely fine, because by giving your angle as a multiple of pi, we automatically know it's in radians. If your angle is in radians and it's not a multiple of pi, so for instance this 2.5 radians that I've used here, you've got to either use the c to show that your angle is in radians, or simply state in words that your angle is in radians. If in doubt, always write down my angle theta is in radians, so we know it's in radians for certain. So have a go at a couple of examples yourselves. I'd like you to convert 1.4 radians into degrees and 0.4 radians into degrees as well. So hopefully you've done this correctly. 1.4 radians is 80.214 ... degrees, and 0.8 radians is 45.836 ... degrees, which of course both can be rounded. So the point of this is just to really illustrate that not all angles in radians are exact multiples of pi. and you've got to be very clear with your notation when identifying an angle in degrees or radians. So the notes at the bottom of this slide just summarise everything we've talked about briefly so far, so do make sure you pause and read these carefully to make sure you understand exactly what we've been going over. So we're just going to take a visual look at some of these angles that we've been working with. So let's remind ourselves, 360 degrees is equal to 2 pi radians. So a full turn on a circle like that, going round, takes us to 360 degrees, or 2 pi radians. If we have a half turn, of course, 180 degrees is equal to pi radians. And if we have a quarter turn, i.e. we create a right angle, like this, then we have pi by 2 radians. So 90 degrees is equal to pi by 2 radians. Now, I think it's interesting for us to actually think about what 1 degree would be in terms of radians. So think about the calculation conversions that we looked at earlier on. Can you work out what 1 degree would be equal to in radians? So 1 degree is equal to pi by 180 radians, or if you actually work that out as a decimal, 0.01745 ... radians, and I'll use the C symbol there to make it really clear that we're working in radians. Now that's visualised in this diagram over here. So you can see there's a tiny angle here in the sector, and that's angle ABC, which is equal to 1 degree, which is equal to pi by 180 radians, or 0.01745 radians. Now, in the last diagram, we're actually going to do this slightly differently. We're going to work out what is 1 radian equal to in degrees. So 1 circular measurement in degrees. Can you work out what 1 radian is in degrees using the conversion? So hopefully you've done the calculation correctly, and you will have found that 1 radian is 57.295 ... degrees. So that's illustrated by the diagram below here, and we can see that angle ABC is equal to 1 radian, which is 57.295 degrees. And you can see that that measurement there is about 57 degrees. It looks just short of 60 degrees there, which makes sense. So that's what 1 radian actually looks like visually, and I think it's important for you to be able to see that. Now, let's go back to this original statement over here, where 360 degrees is equal to 2 pi radians. Now, what is pi? Pi is 3.14 ... as you know, so it's about 3. So we can say that 360 degrees is approximately 6 radians, if we're using the fact that pi is approximately 3. So 360 degrees is equal to 6 radians approximately. Now, go back to this diagram and you'll see that that does actually make sense, because you can just about see how 360 degrees can be split into 6 of these sectors. So if that's 1 radian, that's 1 radian, 1 radian, 1 radian, 1 radian and 1 radian. Now we know it's not exact because 360 degrees equals 2 pi radians, but we can see approximately that there are 6 radians which make up 360 degrees, approximately. Of course, when we're working mathematically, we need to make sure we're using the exact conversion. So remember, always 360 degrees is the same as 2 pi radians, or if it's easier to remember it this way, 180 degrees is pi radians. And make sure you've got a clear way of carrying out your degree to radian conversion. Now your calculator will be involved heavily in this, but we will look at that a little bit later on when we look at trigonometry and radians.